Okay, on this example number 4, we have a uniform 30 kg slender rod is being pulled by the cord that passes over the small smooth pack at A. If the rod has a counterclockwise angular velocity of 6 radian per second at the instant shown, so it is not start from rest, so it has a initial angular velocity of 6 radian per second. Okay, on this particular example, we need to determine the tangential and normal components of reaction at the pin O and the angular acceleration of the rod. To begin with, okay, first we look into the problem that's shown here on this particular figure. The difference between the previous example number 3, what happened is the point O is located somewhere on this rod. Okay, on this particular example, the axis of rotation is at the end of the rod. Okay, that's the difference. And if you can see here that if the axis of rotation is somewhere on this particular rod, what happens is your I O would be 1 over 12 ml squared. But here, since it is at the end of the rod, then it is not like that. It is 1/3 of ml squared. Okay, you can refer to the back of the book for further reference. Okay, on this particular figure, you can see that the rod has a initial angular velocity of 6 radian per second, and there is a rope attached that passes through the point A here, and there is a force 300 Newton, okay, pulling this particular rod. Okay, and if you if you look here on the solution part here, first we need to calculate the tangential acceleration of this particular rod, which is alpha times rg, the angular acceleration times the rg, which is alpha. We know that it is that the things that we are going to determine, the angular acceleration of the rod. Okay, and rg is, okay, again from the previous example, we already mentioned that the total length, the total length is 0.9, and if you put the middle here, should be 0.45, and this part is 0.45. And if let's say this is the center, okay, this is sorry, if this the center somewhere here, and the difference here should be 0.15. Okay, it is our point G lah. Point G is over there. Okay. Okay, now that's why we have 0.45 because it is calculated from point G to point O. This is our rotating axis. So this is the 0.45. However, if you want to know what is the distance between point G and this point of line of forces, I would say, then it is 0.15. Okay, don't get confused on that. Okay, then the normal acceleration, like as usual, you have the angular velocity square times the rg. Okay, angular velocity is given 6 radian per second. Okay, it is start with the initial angular velocity of 6 radian per second, just multiply by the RG, okay, then get this answer, 16.2 meter per second square. Then you need to calculate the mass moment of inertia of this particular rod, slender rod, where the rotating axis is here. You can use the parallel axis theorem to prove this one, but anyway, since we can refer to the back of the book, then can jump straight into that. Then just plug in the value where the M is 30 kg, okay, and then here kg, and 0.9 is the total length of this particular rod, okay, and then you get this 8.1 kg meter square. Moving on, we want to calculate the summation of moment at point O here, okay. Counterclockwise, again, it is a positive direction. Then we look into all the forces involved. Okay, in this case, if I deduce this pipe here, it is 0.8, and down here is 0.6. Okay, 0.8. This one is 0.6. Okay, or we can also say 4. It is 3, and we know that this is a triangle, and therefore here should be 5, right? So here you can put it 3, and this one should be 5. Okay, to further simplify our problems. So now the forces should be here, okay, and there should be the vertical component of it going up, and then another part is going to the left of this screen. Okay, we have a 300 Newton. Okay, there is no pulley involved here. The forces, the P is the same here and as well as here. The total value of P will not change. Okay, but on this part, we want to calculate um, the vertical part of it. Okay, therefore we have a 300 times 4/5. Okay, this part, and this part down here should be 300 times 3/5. Okay, on this part. Okay, for this force, this one, it is going up. So if this is our center of rotation, then it will create a motion like that. So it is a positive direction. Okay, positive. And then the perpendicular distance from here to this point O is given 0.6. Okay. And then what else that we have? We have the mass. Okay. The mass of this rod. Okay. The mass. mg. Mass of this particular rod. Okay. And it is going down here. It will create a clockwise. So it is a negative. Times 0.45 is the distance from point G to point O. Okay, because point G is in the middle between along this rod, 0.45, and then that is equal to the moment of inertia of the rod, okay, that we have already calculated here, up here, times the alpha, and from this particular equation, we can determine this the value of angular acceleration of the rod, which is 1.43 radian per second square. And then, okay, we look into the normal force. Okay, normal force, summation of normal force, and going to the left is our positive direction. And I already put this reference axis to to visualize what is going on, to make it more clear. Okay, now the normal reaction force at point O is going to be like this, going going that way and going this way. Okay, to resist the, to support and resist the point here. Okay, so we have a normal reaction at point O. Okay, going up is positive, so it is positive. Then plus with the force P, Py, we can say it is Py, okay, which is 300. Sorry, not Py. The normal force is in this direction, and then the normal force is positive here, and this the Px, okay, Px. This one is a Px, okay, and then equal to m times the normal acceleration of this particular rod, which is already obtained up here, 16.2. Just then, finally, you can get this value of normal reaction at point O. And we look into the vertical axis, vertical component of this tangential forces. Then we have OT, which is the tangential reaction forces at point O, which is going up. That's why it is positive. And then we also have this PY here that is also going up, and it is positive. Then don't forget that we also have this weight. Okay, and all that equal to the mass times the tangential acceleration of the rod, which is this one is the alpha that we already obtained here, and then 0.45, okay, is the distance from O to G, or yeah, RG, or whatever you want to call it, from here to this center of mass of this particular rod. Then you can do the math. Finally, you can get this value of tangential reaction force at point O. Thank you.